In both lectures 21A and 21B of differential equations and linear algebra, I introduced the very important ideas of eigenvalues and eigenvectors in the context of examples. An example of a two-dimensional linear system of differential equations and also a two-dimensional linear system of difference equations. That continues in this lecture with a lot more detail. We look at more examples. In 22A, we look at sinks, sources, and saddle points, which you might call typical behavior for two-dimensional linear systems of differential equations with real number eigenvalues. We also review the matrix exponential and flows. Those are important here as well. In 22B, we talk more in depth about definitions, theorems, and remarks related to eigenvalues and eigenvectors, including some other topics that you can see there. And we come back to difference equations, and we look at the time one map for an example from lecture 22A, and we think about what happens with the corresponding difference equation in 22B. But let's look at our examples. Let's start with a sink example. So here we have an example of a linear system of differential equations, two-dimensional. Here is our coefficient matrix here, -4, -2, -1, -3. In terms of a system of differential equations, it would be dx dt equals -4x minus 2y, and dy dt equals -x minus 3y. What do we want to do? We want to do what we did in lecture 21A. We want to solve this system. We want to find a general solution. Then we also could use that to solve any initial value problem that we want. I won't actually solve any initial value problem here. I'm more interested ultimately, though, in the phase plane and what's going on in that phase plane. So, as in lecture 21A, we need to look at the characteristic polynomial and the eigenvalues. The determinant of this matrix that you see here, A minus lambda I, where I is the, in this case, 2 by 2 identity matrix, and therefore lambda times I is the matrix that looks like this. And I take A minus that, this again here is A right there. I subtract entry by entry, so in the upper left corner I get -4 minus lambda, like you see there. In the upper right and lower left corners, those stay the same, the values of A, because I'd be subtracting 0. And in the lower right corner, I have -3 minus lambda, this -3 minus that lambda right there. What is the determinant of that matrix? It's a function of lambda. It's a polynomial, a quadratic in lambda. Go ahead and multiply the quantities on the main diagonal and subtract the product of the numbers on the off diagonal. You get -4 minus lambda times -3 minus lambda in parentheses, minus -1 times -2 is +2, so we subtract +2. Go ahead and FOIL this out. The lambda squared term comes from negative lambda times negative lambda, which is positive lambda squared. The plus 7 lambda comes from -4 times negative lambda, which is positive 4 lambda, and -3 times negative lambda, which is positive 3 lambda, to give you 4 lambda plus 3 lambda is 7 lambda. And then -4 times -3 is positive 12, minus 2 is 10. This polynomial here, which is called the characteristic polynomial, can be factored. And generally, you might not be able to factor it so easy. You might have to use the quadratic formula. The roots of this are going to be -5 and -2. When you set that equal to 0 and solve for lambda, you get these two values. I'm going ahead and labeling them with subscripts, though you don't always have to do that, just to keep them distinct. These are two distinct eigenvalues for this matrix, and they're going to help us, once we find the corresponding eigenvectors, to solve for the general solution. How do you find the corresponding eigenvectors? Remember that you think about non-trivial solutions of this homogeneous equation here. That's what I talked about again in lectures 21A and 22A, or excuse me, 21A and 21B. What are the non-zero solutions of this? Because the determinant of this matrix is 0 when lambda is -5 or -2, that's where that matrix is going to be non-invertible, which is called, it's going to be where it's, non-invertible, which is called singular, which means you're going to have non-trivial solutions to this. So you go ahead and you solve for them. You plug in those two values of lambda and see what happens. When you plug in lambda equals -5, right here into this matrix, ignore the determinant symbol. -4 minus -5 is +1. The -2 and the -1 stay as they are. -3 minus -5 is +2. I'm thinking about a homogeneous system of the kind that I erased. I want zeros on the right-hand side. I do row reduction to reduce row echelon form. These two rows are multiples of each other, so the last one becomes 0 after I add these two rows and put the answer in row 2. And I can think of this now as a system x minus 2y equals 0. In other words, x equals 2y if I want to think of y as a free variable. Any non-zero solution of this form where x is twice y will be an eigenvector for the eigenvalue -5. You might as well pick, so to speak, the simplest one. Take y equal to 1 and therefore x will be 2. But I could take any non-zero multiple of this that I wanted to. If I go ahead and write e to the -1 times t, excuse me, e to the lambda 1 times t, which is e to the -5 times t, times the corresponding eigenvector, that is an example of a solution. It's called a straight line solution. If you graph this as a parametric curve in the plane, if you think about it here, in the xy plane, when t is 0, it'll start at the point 2, 1. I can think of that as a point or a position vector for that point. And as t increases, e to the -5 t goes to 0. This solution curve will be on a straight line parallel to that vector, heading toward the origin, which is an equilibrium point as t goes to infinity. You actually can plot it for negative t as well. You can go backwards in time and plot it back there. But as far as drawing arrows on the solution curve, you want to draw them going toward the origin. That's an example of a straight line solution. What about the next eigenvalue, -2? Again, go ahead and plug in -2 here and here. -4 minus -2 is -2. -3 minus -2 is -1. Keep the -2 and the -1 as they are. Once again, we get an augmented matrix where the two rows are multiples of each other. When you do row operations to reduce row echelon form, you get a row of zeros. This line here is equivalent to x plus y equals 0, and therefore x equals -y. Once again, I can think of y as a free variable. Take y equal to 1, then x will be -1, and I can construct my solution to that. This one will lie on a line of slope -1 through the origin, and when t is 0, it'll be at the point -1, 1, and head toward the origin as t increases. In that case, once again, our equilibrium point is at the origin. And once again, you could plot it in backwards time if you like as well, but make sure you put the arrows indicating the direction of motion in forward time as t increases. What do you do to find the general solution? I mentioned now that two-dimensional linear systems like this, the solution spaces as vector spaces are two-dimensional. We have found two linearly independent solutions. These are not constant multiples of each other. Therefore, by the basis theorem, these will also span the solution space. They will be a basis for the solution space. And that means I can write any arbitrary solution as a linear combination of them like this. Y of t equals k1 y1 of t plus k2 y2 of t, a linear combination of those where k1 and k2 can be anything, is a general solution. I can write it this way as well. And then again, I can use this to solve any initial value problem that I want. Set this equal to something when t is 0, solve for k1 and k2. I'm not going to take the time for that. That should be a relatively easy thing for you to do. All right, again, I said I was more interested in the phase plane, so let's think about nullclines. The x nullcline is going to be where -4x minus 2y is 0. In other words, that's where dx dt equals 0. And solutions, non-equilibrium solutions, have to cross that with vertical tangents, either going up or down. It's a line with a slope of -2 through the origin. The y nullcline is where dy dt is 0, which in this case is -x minus 3y equals 0. Set that equal to 0, solve for y, you get a line through the origin with a slope of -1/3. Let's make a quick hand sketch of what we think the phase plane looks like, and then I'm going to show you the computer output for it, which is going to be very pretty, I think. I've done something that I think is kind of nice. But if we need to make a quick hand sketch, the origin is the only equilibrium point. That's where these two nullclines cross. The x nullcline has a slope of -2. The y nullcline has a slope of -1/3, say about like this. You got to cross the x nullcline vertically and the y nullcline horizontally. Which direction do solutions go? You need to think about the signs of these quantities when x and y take on different values. For example, if you're in the first quadrant up here, where x and y are both positive, then both of these quantities are going to be negative. dx dt and dy dt are both going to be negative. Solution curves are going to move to the southwest. On the other hand, when you're down here in the third quadrant, where x and y are both negative, then these quantities are going to be positive. dx dt and dy dt are going to be both positive, and solution curves are going to move to the northeast. In between, you can figure out what goes on as well. And if you think about it, in this wedge in here, you got to be going to the northwest. And in this wedge, we've got to cross those nullclines correctly. We've got to be going to the southeast here. Got to cross that nullcline horizontally. It's difficult to make perfect pictures for these things, but do your best to make a decent picture. Get something about like this. And there are straight line solutions, like I drew here. There's a straight line solution coming in about like this, also one coming in about like that. In fact, these are on the same line through the origin. And you're going to have ones going in here and in here. That's a very quick sketch of what this phase plane looks like with the solution curves and the nullclines drawn. But let's make a really nice looking picture with Mathematica. I did that ahead of time. Here's the phase plane for the sink. I'm also going to note something else that's kind of subtle. Most solutions approach the origin as t goes to infinity asymptotically to the straight line solution for the eigenvalue closest to 0. That's a mouthful. What do I mean here? Well, this line of straight line solutions corresponds to the eigenvalue closer to 0. That was lambda 1, or maybe I called it lambda 2, equal to negative 2. This one was lambda 1 equal to negative 5. And that one's closer to the origin, and you can see most solutions are approaching the origin tangent, asymptotically tangent to that straight line, not this straight line. In fact, this straight line is the only set of solutions that do not approach the origin asymptotically to the other one. Okay, that's what I mean by most, is everything except along that other straight line here, all looking like this. Here's what the picture looks like when you use Mathematica and vector plot and stream plot, and added a big dot at the origin for your unique equilibrium point at the origin. And by the way, the fact that that's a unique equilibrium point is related to the fact that the determinant of the coefficient matrix is non-zero. For my students, they might want to look into that as far as the reading goes. There's your picture. The red arrows are scaled down versions of the vector field. They are all straight. The blue arrows are supposed to represent solution curves. They are not all straight. The straight line solutions, again, are those coming in about like this, about like this, about like, it's about like this, say, and about like this. Those are straight line solutions, not the same as the nullclines, right? The nullclines are not straight line solutions. They only help you draw the picture. That's the purpose of the nullclines that I've got in brown and pink here. They only just help you draw the picture. They are not solutions. Make sure you don't make that mistake. And we are approaching this line of straight line solutions asymptotically. Every solution except for the ones along this line. Why? Because intuitively, you think about the formula for the solution. It involved, again, k1 e to the negative 2t times, what was it, negative 1, 1, I think, plus k2 e to the 5t, or negative 5t, I might have had these switched around, times 2, 1. Again, I might have had those switched around. As t gets bigger and bigger, the exponential decay with the coefficient of t more negative goes to 0 a lot faster, so to speak, than this one does. So when t is large, both of these are close to 0, but the solution curve is a lot closer to being along this line than it is to being along that line. That's the intuitive reason why they approach asymptotically that way. That helps you get the picture more accurate. Our textbook gives a little bit more rigorous reason for that. Next example, source example. For the source example, I'm taking the easy route, but I also am trying to make a point here. The example I'm going to consider is the exact opposite of the previous example. The matrix here, all I did was just change the sign of all the numbers. Essentially, I multiplied the matrix by negative 1 to get this vector field. Think about that. What should happen? Are you back? Did you think about it? All the vectors in the vector field, the red arrows, are going to get switched in direction. They'll still be parallel to the other one, but in the opposite direction. So it should make sense that this gives a source instead of a sink. You might have guessed that the first one was a sink and this one was a source because the first one had all negative coefficients and the second one had all positive. That can be misleading. Don't always assume that's the case. In fact, we're going to see another example, the example from 21a, where all the numbers are positive, but not all the eigenvalues are positive. So don't take that too literally there. The characteristic polynomial and eigenvalues here are kind of similar to the previous example. In fact, the eigenvectors are the same. The eigenvalues are opposite signs. Here's the way the eigenvalues work out. What's different? It is a different matrix. It is a different determinant. What changed was this was a plus sign with the previous example, and it becomes a minus sign here with this new example. Making it, instead of lambda plus 5 times lambda plus 2, lambda minus 5 times lambda minus 2. The eigenvalues, instead of being negative 5 and negative 2, are positive 5 and positive 2. But the corresponding eigenvectors are the same. That should make intuitive sense as well. The straight line solutions will still be straight line solutions, but now in the opposite direction, because the arrows get switched in their direction. We find the corresponding eigenvectors, we get the same eigenvectors as before. The 2, 1 and the negative 1, 1, I guess, yes, I did have them switched around in the other order. And we get 2 straight line solutions, but now these straight line solutions, as t increases, go away from the origin. As t decreases, they go toward the origin, but draw arrows going away, because we want to think about t increasing typically. This one is going away from the origin as well, as t increases. Again, you could draw it as t goes to minus infinity as well, and in fact we do draw that in when we make the phase plane, but draw arrows going away from the origin there. The origin is a source now instead of a sink. The general solution has a very similar form. The only difference here is that we have positive eigenvalues instead of negative. By the way, I did mention a few minutes ago, general solutions are actually not unique. I can take any non-zero multiples of these eigenvectors and get other eigenvectors and other straight line solutions. But those other straight line solution sets would form still a linearly independent set of solutions that would still span the solution space and still be a basis of it. I could multiply these vectors by any non-zero constants and it would still be a general solution. Does that contradict uniqueness? No, because if you solve any initial value problem, the solution will still be unique. General solutions can be written in different forms, but solutions of initial value problems, when they are unique, as they are in these examples, will be the same formula, at least if you simplify appropriately. Nullclines are actually the same as before as well. Think about these being 0. If you solve for y as functions of x, you get the exact same nullclines. This is still the x nullcline, this is still the y nullcline, though you're going to cross these nullclines in different directions than the previous example. It's essentially this picture with all the arrows reversed, still with an equilibrium point at the origin, a unique equilibrium point because this matrix has a non-zero determinant. And you still get the same asymptotic behavior this time, however, t goes to minus infinity instead of plus infinity. Here's the picture. Again, it's just a turned around version of the other picture. By the way, I wanted to emphasize this with the other picture, but I forgot to. I'm using some color coding here that I want to stay consistent for the rest of the semester, for the rest of the course. I want light pink shading to represent solutions that move to the northeast, as these do. I want light blue shading to correspond to solutions that move to the northwest, as these do. Light green shading for solutions that move to the southwest, and light yellow shading for solutions that move to the southeast. I'm going to try to keep consistent with that for the rest of the semester, not only with linear systems like this, but also even with nonlinear systems and their phase planes. I think that'll be a nice way to think about things. The nullclines separate the different shading regions. I used pink and brown for the nullclines. I'm not sure that I'm always going to use pink and brown for the nullclines. Let's compare. These are opposites of each other. The vector fields, again, point in opposite directions. It's nice to look at them and compare. These are somehow complementary to each other, you might say. Okay? I didn't have to do it that way. I could have picked a completely new example. But to make an educational point, I decided to take these opposites to illustrate this fact here. All right, now let's consider the linear system from lecture 21a, this one here, whose entries are all positive, that might make you think, oh, the origin's got to be a source. But you'd be wrong. As we saw in 21a, there's one positive eigenvalue and one negative eigenvalue. The eigenvalues, I'm not going to take the time to do the details because I did that in 21a, are negative 1 and 4. One negative and one positive. The corresponding eigenvectors, which you should check as well, are negative 3, 2, and 1, 1. This is the general solution. These are still, ignore the k1 and k2, these are still linearly independent solutions. The solution space for such a two-dimensional linear system will be a two-dimensional vector space, as a vector space whose elements are functions. By the way, I didn't emphasize, but I'm emphasizing now. And that means by the basis theorem that these two functions will stay in the solution space, they will be a basis for the solution space, and therefore a general solution is an arbitrary linear combination of them, or any non-zero multiples of them. General solutions are not necessarily unique. They are related, but not unique. But if I solve an initial value problem with this, I will get a unique answer because of the uniqueness theorem, though it might not look the same as somebody else's answer at first, but if you both do it right, you should be able to simplify it to the same thing. What does the phase plane look like? Looks like this. The origin is now called a saddle point. Oops. Higher dimensional nodes are not called nodes anymore. They're called saddle points. Well, there are certain kinds of things that you still might want to call nodes. But this kind of picture, you want to call the origin a saddle point. Straight line solutions corresponding to these eigenvalue-eigenvector pairs. Focus first on the negative 1 eigenvalue, corresponding eigenvectors negative 3, 2. Eigenvectors always go with one eigenvalue, not the other. That corresponds to a straight line solution about like this here and about like this here. Stop. And it's a negative eigenvalue. Arrows are pointing toward the origin. It's a sink in that direction, so to speak. And notice that it's parallel to this vector. This point right about here, for example, is negative 3, 2, approximately. For the other one, 1, 1, the eigenvalue is positive. Solutions are moving away along that line. It's a source in that direction. Overall, though, it's neither a sink nor a source. It's some sort of weird combination of the two. Solution starting over here, head up this way, crossing this brown nullcline with vertical tangents. That's the x nullcline there, the brown one. Solutions down here go this way, crossing the pink one with horizontal tangents. That's the y nullcline. Similar kinds of things in here. My students, you should be able to try to draw these by hand reasonably quickly. It takes some practice. The nullclines can help you. I would encourage you to draw nullclines on your own. On exams, I might give you the nullclines. All right, most solutions don't approach the origin either as t goes to plus infinity or minus infinity. Solutions along this line approach the origin as t goes to plus infinity. Solutions along this line go away from the origin. They approach the origin as t goes to minus infinity in backwards time. Okay? That's called a saddle point. Why is it called a saddle point? Well, it's kind of reminiscent of the fact that when you sit on a horse's saddle, the saddle goes down in the direction of your legs and up in the direction this way of the horse's back. And it's kind of a similar feel. If you imagine solutions kind of going downhill, you might say, you'd be sitting on the horse kind of like this. Imagine me going sideways. If solutions are going downhill, down the saddle, you'd be sitting on it this way with your legs going this way and this way. And the back of the horse would be going that way. Okay, that's why it's called a saddle point. It's related to saddle points in multivariable calculus as well. Continuing. All right, now I'm wanting to bring this into the realm of the matrix exponential again. And flows, to re-emphasize that content, that I've emphasized recently. Those are difficult content, but it would be good to think about it in the context of simpler examples like linear systems here. If you solve a generic IVP, what do I mean by that? I mean y of 0 equals y sub 0 equals a vector whose components are little x0 and little y0, and I pretend those are fixed. It gives me this solution. I'm not verifying this. You might want to take the time to verify it. How? Well, use the general solution for the saddle point example here, the one from 21a. Plug in t equals 0. Set it equal to x0, y0. Solve for k1 and k2. Evidently, you should get k1 to be negative 1/5 x0 plus 1/5 y0. And k2 to be 2/5 x0 plus 3/5 y0. Try it. We can plug in what y1 and y2 are to get that. And then we can write this as a matrix times the initial condition. Why? Because we can rewrite it like this. I did this before as well. For example, where does this vector come from? It comes from, first of all, the combination of these things and the combination of these things. Negative 1/5 times negative 3 is positive 3/5 x0. That's where that positive 3/5 comes from. I have an e to the negative t as well. And 2/5 x0 times e to the 4t times 1 gives you that term right there. For the second component, I have a negative 1/5 times 2 times e to the negative t. Gives you negative 2/5 e to the negative t. And then also 2/5 x0 e to the 4t times 1 gives you this one. Do something similar with the y0s. And now this is a linear combination of two column vectors. These are 2x1 column vectors. A linear combination of those with x0 and y0 is the way. It's by definition a matrix times a vector. That's this matrix times this vector. This is a 2x2 matrix here. Right? Here's your upper left entry, upper right entry, lower left entry, lower right entry. Those columns of that matrix are the same as these vectors. Emphasize that a lot. Okay, so you can do that. Is this the matrix exponential times the initial condition? You remember when I talked about matrix exponential before? Oh, what was that? Lecture 16a maybe? Remember when I did that? And you're like, what in the world is the matrix exponential? It's still kind of what in the world at the moment, but I will show you more detail that will make it a little bit more precise. Is this true? Is y of t, this function here, e to the t times a times the initial condition, where e to the t times a I could write like that times the initial condition. Is this thing equal to this thing? That's what I'm wondering. If a is a matrix, t times a is a matrix, and e to the ta is another matrix. Well, let's just use Mathematica to check and see if this is right. So we are on our saddle point example here. By the way, eigensystem in Mathematica like this can compute both eigenvalues and the corresponding eigenvectors. For this saddle point, eigenvalues are 4 and negative 1. The eigenvector corresponding to 4 is 1, 1. Eigenvector corresponding to negative 1 is negative 3, 2. But again, I could have taken any non-zero multiples of those as well by hand. And Mathematica won't necessarily always pick the ones you pick. This code generates the picture. I'll let you look at this if you like. There's the picture. Oops. Here we go. There's the code if you want to look at that. Though we'll put it in the Google Drive. Let's look at the matrix exponential here. MatrixExp. How about that? Does matrix exponentials. Matrix form makes it look like a matrix. Is that the same matrix as before? Looks kind of familiar. 3/5, 2/5, negative 3/5, 3/5, negative 2/5, 2/5, 2/5, 3/5. Let's see. We've got e to the negative t's and e to the 4t's. Are those the same? 3/5, 2/5. Yeah. Oops, look here. Right there. Yeah, I think it's the same. Yeah, looks good to me. So Mathematica says yes, it is. MatrixExp is what did that. But wait a minute, what exactly is the matrix exponential? What is it? And why does that work? This is not going to be a full justification, because I'm not going to fill in all the details. There are details, plenty of details to fill in, but I'm giving an outline justification of why that works. To define the matrix exponential, you need Taylor series. Recall the Taylor series for e to the x centered at x equals 0, also called the Maclaurin series for e to the x, is this. Should have seen that in your past. If you're in this class, you should have seen this in second semester of calculus, or maybe second year of calculus. E to the x is 1 plus x squared over 2 factorial, plus x cubed over 3 factorial, plus x to the 4th over 4 factorial. Right, 4 factorial, for example, is 4 times 3 times 2 times 1, which is 24. The next term would be x to the 5th over 5 factorial. 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. By the way, even here you have factorials. This is the same as 1 divided by 0 factorial. 0 factorial is defined to be 1, not 0. So I'm not dividing by 0 there. Partially it's defined to be 1 because it makes this formula work out nicely. 1 factorial is also 1, so I could write that there too. I can write it with summation notation like this. And this turns out to be true. This series converges and equals e to the x for all x. That is one of the most astounding things in all of math, right there. If you were never astounded by it, well, change your perspective. Be astounded. This is amazing. Why in the world would that be true? Serious. Why would that work? Who would ever expect, if they didn't get taught about it, that that would work? With the matrix exponential, we do the same thing, except we replace the number x with the matrix t times a, and we also replace the number 1 at the start here, is what I mean, with the identity matrix I. And write that. So e to the ta is this infinite series of matrices. These are all matrices. By the way, here I am thinking about the general case. I'm assuming a is not necessarily just 2 by 2, but say n by n, where n can be any positive integer. It's going to be a million by million matrix here. These are all matrices. The I, the a squared, the a cubed, a to the 4th are all matrices. The t's and the t squareds over 2 factorial, etc. are all scalars, but a scalar times a matrix is a matrix. You multiply entry by entry. These are all matrices. They're all being added up into an infinite sum of matrices. This should seem kind of fishy. Can we really do this? This should raise questions in your mind. What does this even mean? Can an infinite sum of matrices really converge like infinite sums of numbers? If it can converge, what would it mean for it to converge? Is this a good idea? Is it useful? We will mostly take an intuitive approach to the questions of convergence by looking at partial sums and seeing whether they seem to converge or settle down towards some specific matrix. I'm not going to prove things by any stretch of the imagination there. Just take an intuitive approach. If you wanted to prove it, that's pretty advanced. It's like senior level math, maybe graduate level math to verify convergence. It's related to norms, actually, but norms of matrices instead of norms of ordinary vectors. We have talked about norms briefly. However, it is certainly useful by what I call, this is my terminology, kiddie terminology, the beautiful generalization. What beautiful generalization do I have in mind? It's a generalization of this fact that I did mention last time, actually, 21a, or was it 21b, I don't remember. The unique solution of this scalar first order autonomous ODE, linear, is going to be y of t, say, well, let's go ahead and use the phi notation. Y equals phi sub y0 of t equals y0 times e to the a times t. We've seen that a lot. That generalizes to this. The unique solution of this vector IVP dy dt equals the matrix A times y, where in general y is an n-dimensional vector, and A is an n by n matrix. It's got to be square. And I've got this initial condition. The unique solution is the same kind of thing. Except, say, use a capital phi instead of a lowercase phi because we're talking about an Rn here. Use e to the t times capital A as a matrix exponential, not a number e to the at. The initial condition vector I put on the right because I am taking an n by n matrix times an n by 1 vector. The vector's got to be on the right if you treat it like a column vector. It's not that I couldn't write the y0 on the right here. It's just not traditional to. I could write this as e to the at times y0 if I wanted to. Why do I put the t in front of the a? Actually, I didn't do that initially when I first talked about the matrix exponential, but it is more traditional to put the t in front of the matrix capital A here because it's more traditional to put scalars on the left side of vectors and matrices than on the right side. But that's just a matter of style. Isn't that beautiful? I give it this name, the beautiful generalization. It's one of the most beautiful generalizations in all of math, I think. Plenty of people might disagree with me, but I give it that title. That's Kinney's title for this, the beautiful generalization. Why is the beautiful generalization true, though? And we're setting aside questions of convergence. What else might we begin setting aside? Well, that we can differentiate this thing to check that it works in what you might call a natural way. What's the derivative of that solution? dy dt, it's capital Phi prime. Plug in the matrix exponential times y0 to get this. And then replace e to the t times a with its infinite series. And assume you can differentiate term by term. That's stuff that I'm putting under the rug and not worrying about. What would happen if you differentiate term by term and keep the y0 as a constant out over there on the right? You'd get this. I doesn't depend on t. Its derivative is 0. That's actually not the 0 number or the 0 vector even. That's the 0 matrix. The matrix, the n by n matrix with all zeros, because all these things are matrices. T times a, what's its derivative with respect to t? I guess it would just be a. T squared over 2 factorial times a squared, what's its derivative with respect to t? Bring the 2 down in front and keep the 2 factorial and the a squared as they are. Same kind of thing here and here to get this and this. What next? Well, 0 matrix can go away. Everything that's left does involve a factor of a that can be factored out. What's left after factoring out? Well, I is a times I. A times I is a, is what I meant to say, sorry. A times t times a is t times a squared. The 2 factorial, the 2 and the 2 factorial partially cancel, in fact, fully cancel since 2 factorial is 2. A cubed times t squared, I can factor out one of those a's and get a t squared times a squared. And 3 divided by 3 factorial is 1 over 2 factorial. 3 factorial is 3 times 2 times 1, so a 3 cancels. Same kind of thing happens here to get this. And wait a minute. That's the same as a times e to the ta, the matrix exponential, times y0. Hey, that's a times the proposed solution function. It equals the right-hand side for all t. Done. Assuming I can do all this. You know, engineers, scientists don't care to prove things like this. Typically, at least, they trust it if a mathematician says to trust it. They shouldn't. They really should try to verify things from scratch to convince themselves, if nothing else. But it turns out you can justify all this. The mathematician is telling you. Also, it satisfies the initial condition. Plug in t equals 0 as a scalar 0. These zeros are all scalar zeros, so I can do 0 squared. Well, okay, yeah, these are all the number 0, but that makes all these things the 0 matrices. And I plus a bunch of 0 matrices is I So we get I times y0 is y0. Satisfies the initial condition. It works. Okay? I think this is pretty cool stuff. I also like the graphs earlier. One main thing left to do here in lecture A, and that is to relate this to flows and difference equations, as I've talked about recently as well. Though I talked about it recently in the general nonlinear case, but now it's simpler. It's the linear case. And time t flow maps in this case are actually going to be linear transformations. Time t flow maps for nonlinear systems are not linear transformations. Recall the time t flow map for fixed t is this. Once again, I emphasize, it's just a change in perspective. There's your solution, thinking of y0 as fixed and t as the variable. But now, for the time t flow map, I'm thinking of t as fixed and y0 is the variable. The initial condition is the variable. The graph of this is a parametric curve in the plane if it was a two-dimensional system, in space for 3 and higher dimensions. You can't really graph this in the usual way. You've got to think about it as a mapping, because it's a linear transformation from R2 to itself or Rn to itself in general. And because it's a linear system, we can relate it to the matrix exponential. The formula here is e to the ta times y0. You want to think of it as a solution, think of t as the variable, a and y0 are fixed. You want to think of it as a flow map, think of y0 as the variable, t and a are fixed. And it is a linear transformation. If this is an n by n system, then it's a linear transformation from Rn to itself. In fact, it's even invertible. What's the inverse of this linear transformation? It's this. The inverse of the time t map is the time negative t map. We actually haven't really talked much about negative time flow maps, but we could. And it is worth thinking about sometimes. And so that means this is true. The inverse of this matrix is this matrix. That's true as well. You might want to think about confirming that you can verify these things. Okay? In general, when you've got flow maps that are defined for all times, these kinds of things, this kind of relationship will still hold actually, though this is not an inverse of a linear transformation. In that case, it's an inverse of a nonlinear transformation. Again, if we have flow maps for nonlinear systems which are defined for all times, this kind of thing will hold, but not this, because you won't have a matrix exponential in the nonlinear case. Remember, I also emphasize the importance of the time t flow maps. In particular, we usually look at the time 1 flow map to generate a difference equation whose solution is very much related to the solution of the differential equation. Here's our recursive equation, a difference equation for yn in terms of yn minus 1. Took t to be 1, time 1 map, which means t is also 1 right here. And you just get e to the a times yn minus 1. If you iterate this, you get the solution, and it does match the solution of the differential equation. Okay, though there's some things that need verification there as well, like is this true? Is e to the a times e to the a plus a, which we call e to the 2 times a. Is that true? It turns out, yes, it is true. Though in general, if I have e to the a times e to the b, where b is some other matrix, I can't necessarily add the exponents, the exponent matrices, it turns out, unless it turns out a times b equals b times a as a product of 2 matrices. Then you can add the exponent. I'm not going to get into that. With the help of Mathematica, we can compute formulas from this. And we can also use this information to animate how sets get mapped under the flow for the system of differential equations. I'm going to do that in lecture 20, at the end of lecture 22b. So yes, make sure you watch lecture 22b as well. See you later.